Hello everybody, welcome to the course VLSI Design Flow RTL to GDS. This is the 7th lecture, and in this lecture we will be continuing with the overview of VLSI Design Flow. So, the topics that we will be covering in this lecture are verification and testing. In the earlier lectures, we have seen that how to implement a design. Implementing a design means that we are making changes to a design. We started with an idea, then we carried out our system level design, and then we got an RTL, and then we flowed, or we went through RTL to GDS flow, and at the end of this we got a GDS or the layout. So, in this transformation from RTL to the layout, a design goes through various EDA tools. It also goes through various individuals or teams, right. So, during this transformation and during this design phase, error can get introduced inside in our design. And what could be the reason of the error? There can be many reasons. Some of them can be, say, human error or miscommunication between two teams or two individuals within a same team, or it can be wrong uses of a tool, or there can be some unexpected or a buggy behavior of a tool, right. So, these are a few examples what can go wrong in this implementation flow, and to check that whether we have not made any mistake or the design is still good, we need to carry out the verification step along with the implementation step, and this is what we will be covering in this lecture. So, what is verification? We perform verification to ensure that the design works as per given functionality. So, the functionality is defined at the top level, right, and we ensure that our design as it is transformed in the VLSI design flow, it should still be delivering the same functionality that we started with or that was given to us. And to ensure that, we need to carry out verification multiple times throughout a VLSI design flow. So, whenever their design goes through some changes, some non-trivial changes, we must verify that the change is correct and the design is still behaving correctly or delivering the required functionality. And we need to do it multiple times because we want to catch an error or if there is a problem in our design as soon as possible. Why we want to do that? Because then it allows us to fix this problem, and as the quicker we fix the problem, meaning that earlier we fix this problem in the design flow, the fix can be done in with less design effort or less effort in terms of time. So, whenever there is a verification failure, we need to take a remedial action, and if this remedial action is taken as soon as the error is introduced in the design, the cost of fixing that design bug is limited or that is less, right. And that is why we want to carry out this verification stuff throughout our design flow and catch an error or verification problem as soon as possible. So, currently a lot of effort goes into actually in verification, right, and with the advancement in technology and adding of more features in our design, the verification effort is actually increasing with time or with the increasing design complexity. So, verification plays a very important role in VLSI design flow, and in this lecture we will get a look into a top level view of all the verification methods or most important verification methods that we use in VLSI design flow. And in later lectures, we will look into these verification tasks in more detail. So, here we are just getting an overview of what are the verification steps that we need to carry out for a in a VLSI design flow. So, at the top level, when we are given a functionality, we write an RTL model, or we get an RTL model through, say, behavior synthesis, or through IP, that we get it from the vendor, right. So, now the RTL that we have got or that we have designed, that must match or deliver the functionality as it is given in the specification, right. So, to ensure this, what do we do? So, the most common method to ensure that the RTL is as per the given functionality or specification is the most common method is simulation. Okay. So, simulation is a technique for ensuring the functional correctness of an RTL using test vectors. Now, what are test vectors? So, test vectors are sequences of zeros and ones and the associated timing information, meaning that when the transition happened from 0 to 1 and so on. So, test vectors are the stimulus we apply to the design. So, and using the test stimulus, we verify that whether the functionality of our design is correct and matching the specification or not. So, there can be many different frameworks under which simulation can be performed. One of them is as shown in this figure. So, what we do is that we apply test vectors or stimulus to our design, which is in the RTL form, and then take it through a tool which is known as simulator, right. So, simulator gives us, or it basically computes mathematically, that given this test vector and the RTL model, what will be an output response. It will be computed by the simulator, right. And for the same test vector, we also compute the expected output response from the given specification, which may be in terms of say, or which is modeled in C, C++, MATLAB and so on. So, we get this expected response just by running their binary or executables. So, we have a pair of a set of output response that we are getting from the RTL, and we also are getting expected response for the same test vector from our specification. And we compare both of them. If they compare, after comparing we find that these two are same, then we say that the verification has passed or our RTL model is meeting the specification. Now, this is this simulation based verification is very fast, and also it is a versatile, right. Versatile by I mean that this simulation method can be used at various level of abstraction. So, here I have shown it is being used for RTL model, but we can also, instead of an RTL model, we can take a gate level netlist to do a kind of simulation and see that what the output response is. Similarly, we can do this kind of simulation at the transistor level, right. So, simulation is a kind of a very versatile method or technique of verifying a design or a model, right. And it is also very fast, right. It is same as running an executable. When we write as a computer program, we after compiling it, we see that whether that program is producing the correct answer by running it on a given input. So, simulation is a similar kind of method, right. For a given test vector, we are saying that whether our model is producing the expected response or not, right. But what is the downside of this functional verification using simulation? This is a very simple technique, but the downside is that it is incomplete. Incomplete in the sense that the test vectors that we give to during simulation, those test vectors cannot be exhaustive. By exhaustive, I mean that all possible test vectors are if we are giving to a simulator, then we say that it is an exhaustive. But for industry scale design or a practical design, it is simply impossible to give all possible test vectors. Why it is impossible? Because the number of test vectors will be simply be exponential in number of inputs, right? And then there are many other possibilities which comes because of the state elements or flip flops in our design, and therefore covering all possible scenarios is simply impossible. And therefore in simulation what we give as test vector is typically in a region of operation of our model where we think that there could be a bug, right. So there may be some corner cases which we may be simulating, or an area which we think that is a brittle area, or where some errors can be there, or some area of our code or our model where lots of computation is done and which are more vulnerable to bugs. So we typically choose area where we want to simulate and do the simulation accordingly, right. So in that sense, functional verification using simulation is incomplete. So there are alternative ways to do the functional verification. One of the alternative is model checking. So what is model checking? So in model checking also we check the functionality of a design and see that whether it is matching the specification or not. But the difference between model checking and the simulation based checking is that in model checking we use typically formal methods. And what are these formal methods? So formal methods basically establish the proof of a given property using formal mathematical tools such as deductions. Rather than relying on the test vectors, it is trying to prove something mathematically. And so once we have proven a property mathematically, it is guaranteed to hold for all the stimuli. Why it is guaranteed to hold? Because it implicitly covers all the possible scenarios. Let us take an example and understand that what is the difference. Suppose a property is given that a function, a Boolean function fx is equal to gx, and we need to verify it. So in simulation what will be done is that we will try for different values of x and we will see that what f is producing, what g is producing, and match the output of these two functions, and based on that we say that the function fx and gx are equal. But we cannot always cover this gx. For example, if it is the possible all integers, then it is simply impossible to cover all the integers, right. On the other hand, what formal methods will do is that it will try to establish a mathematical proof. For example, it will try to say that can I prove fx implies gx and gx implies fx. If the tool is able to establish this property, then we can say that fx is equal to gx no matter what x is, right. So implicitly it is covering all possible scenarios, right. So the verification using formal method is, the merit is that it offers completeness, but this is the demerit is that it is computationally difficult. We cannot apply this model checking for all kinds of problems. There are computational difficulty in establishing this mathematical proofs. Now in property checking or in model checking, what do we do as a designer? So as a designer we define properties that must be satisfied for a given specification, and then the tool will check whether those properties are being satisfied in the implemented design RTL using formal methods. Now what could be these properties? Let us see a few examples. For example, if you are designing a say traffic controller, then we can define a property that not more than one light should be green, right. So this is a property which should always be true for a traffic controller that is generating a signals for various lights on in a traffic light, right. Similarly, in a resource sharing environment there can be a property like request for a resource should be granted eventually, right. So, this will ensure that the request some requester is not starved of the resource, right. So, these are some of the example of these properties. Now, for a given design or specification, from that we can extract important properties which must be satisfied by that model or an RTL model or our design, and specify them and give it to the model checking tool, and that model checking tool will try to prove it that whether the given property is true for all cases, right. So, again point to note is that it will not do simulation and find out that whether those properties are satisfied for all possibilities. It will use mathematical deductions or mathematical properties to arrive at a argument or arrive at a proof which establishes that the given property holds, right. So, during the design flow, a design goes through various steps of transformation. Now, for example, during when we do logic synthesis, our design was in term of RTL, right, and at the end of logic synthesis we get a netlist. Now, how to make sure that functionally this RTL and the netlist are delivering equivalent function? To do this, we use a tool which is known as combination equivalence checking tool. This tool basically establishes the functional equivalence of the two models, in this case RTL and the netlist, using formal methods. So, combinational equivalence checking or CEC in short required when is required, or we need to run these CEC tools whenever we make non-trivial changes to the design. Why? Because the transformation can introduce bug in our design, right. So, we need to carry out this kind of combinational equivalence checking throughout our design flow, right. So, to just give you an illustration that how do we use combinational equivalence checking, we can start with say an RTL and netlist. So, first thing we discussed that we had a functional specification, right, functional specification. We established that this functional specification was being delivered by this RTL using simulation and also using model checking. Now, after we have got this RTL, we do logic synthesis, and then after doing logic synthesis, we do an equivalence checking between an RTL model and the netlist. And if we establish the equivalence, we in a sense also establish that our netlist is meeting our functional specification. Why? Because our RTL was originally meeting our functional specification as verified by simulation and model checking. Similarly, as the design progresses through say floor planning, placement, clock tree synthesis or routing, if we ensure that combinational equivalence checking is being, or we do combinational equivalence checking between two consecutive steps, and we do this throughout the flow, we can ensure that the final design or the layout that we are having, that meets the functional specification that we started, right. Why we can? Because if there is an equivalence, anywhere there is an error introduced by the tool or by human, that will be caught in this combinational equivalence checking step, right. If we do combinational equivalence checking subsequent steps, we are sure that the functionality that we are getting is equivalent to the RTL, and RTL was originally meeting the functional specification. So, all the transformations are correct in terms of functionality. Now, in addition to functionality, we also need to worry about the timing of our design. Now, in asynchronous design, how do we ensure that the data transfer between flip-flops, for example, if we have a flip-flop and then this data goes from this flip-flop through a combinational logic to a sequentially adjacent flip-flop, then how ideally in a synchronous circuit, the data that is launched at this launch flip-flop must be captured at this capture flip-flop in the next clock cycle, right. That is what the synchronous behavior is, right. Now, the delay of this combinational logic can disturb that behavior, but we need to ensure that it is not disturbed, right. The synchronicity of the data launched by flip flop gets, so by synchronicity we mean that the data launched by a flip flop gets captured in the sequentially adjacent flip flop in the next clock cycle, and this is ensured by a tool which is known as static timing analysis tool, or STA tool. So, it ensures deterministic synchronous timing behavior in a circuit. It will also look into, say, setup and hold constraint of the flip flop to, and if those are broken or those are not violated, it will be reported by the tool, right. Now, STA tools considers the worst case behavior, and which may be pessimistic, it may not be realistic, but more pessimistic, but while producing the result, and therefore, what we can say is that STA, if a design passes STA, the design will always be safe, right. It will err on the side of pessimism, not on the side of optimism, right. So, that is why ensuring the timing of timing behavior of our design and checking it with STA tools is very important. And in a design flow, this is carried out multiple times, right. When we have done, say, we have got the net list, right, then we need to basically do a timing analysis. So, this is the timing analysis tool in which the design can come at various levels of abstraction, maybe at the net list or floor plan design or place design or design that we get after clock tree synthesis or globally routed design or detailed routed design, or even after ECO, we can give design to an STA tool in various abstraction level. And we also need to give constraints to the STA tool. What do these constraints contain? These constraints contain information about what is the expected timing behavior in terms of maximum operable frequency for a design. What are the characteristics of the signals that come into our chip or our design, and what is the expected behavior of the signal that leave our design. So, these things are described in this constraint or constraints file, right. And we also need to give the library which contains the information of the standard shells which are used in this netlist, and based on the library information, the static timing analysis tool will do delay calculation, and based on that it will give us the timing report, and based on this timing report we will see if there are violations, then we might need to fix our design or make changes in our design and then progress to the next steps and so on. Then when we do physical design, then we have to be careful about how we are laying out the components on our design. Then we have to ensure that the layout does not have any manufacturing and connectivity issues, and the yield that we will be getting out of this design will be acceptable. And to ensure this, there are a set of checks that needs to be done during physical design, and those are known as physical verification tasks. So, these tasks are carried out before sending a design to the foundry for fabrication. Some of the physical design verification tasks are design rule check or DRC. So, in this DRC checks, we check for the rules that are coming from the foundry, and we ensure that those rules are taken care of, or those are followed by our design in the layout. If there are any DRC violations, then we need to fix them before sending the layout to the foundry for fabrication. And then we need to do electrical rule check in physical design. So, these are electrical rule checks are basically rules that define and ensure the proper connectivity. For example, if there are two wires, right, which are different wires, they should not short among themselves, right. If there is shorting because of some design error or layout error, then that should be found, that problem should be found and fixed. So, those kind of problems are caught in electrical rule check. And then we also need to carry out a layout versus schematic check, meaning that we need to ensure that the layout that we have created, the transistor level layout, right, that is actually meeting our original functionality that we started with. And this is done using a physical verification task, which is known as layout versus schematic check, or LVS check. In addition to these checks that I have described, there are some rule checkings that needs to be done in VLSI design flow. Now, what is rule checking, or what are these rules? So, rules are some restrictions imposed on the design entity, such as RTL, constraints, netlist, layout, etc., such that there are no issues in using that design entity downward in the VLSI design flow. Right. So, what is the framework of rule checking? The framework is shown in this figure. So, there is a rule checker, and in this rule checker there are some patterns defined, right. Patterns defines that if this pattern exists in our design or in our constraints, then flag an error, right. So, this rule checker will look for those patterns in our design and constraint and flag if those patterns are found in a violation report, and then we have to look into those report and perhaps make some fixes if it is required, right. So, these rules can be defined at various levels. For example, at the RTL level there can be rules which ensure that the RTL constructs used in the design have no synthesis simulation issues, or will not create any synthesis or simulation issues down the flow. Now, these restrictions are more stringent than what is imposed by the language, right. So, the language may allow some constraint, some constructs, but those constructs may be actually flagged by this RTL, so RTL rule checker, because those constructs can cause problem later down the flow. Maybe it may be creating, say, a simulation synthesis mismatch or similar kind of problem, right. So, these rule checkers are more restrictive than what are allowed by a given hardware description language and so on. Then there can be rule checking on the constraints, that if we write these constraints in a format which is known as synopsis design constraint, or SDC format, right. Now, when we give this SDC tool, or sorry, SDC file or constraint to the tool, right. Now, these SDC constraints or SDC files are typically manually written or at least edited, right. Now, while making these changes or writing these SDC files, we can make errors, we can add conflicting constraints and so on. So, if that happens, then it will be flagged by this constraints checker. It ensures that no conflicting constraints are applied or any constraint is missing in our SDC file, right. Then there can be rule checking at the netlist level, which ensure that the connectivity of the instances do not cause any issue down the flow. For example, there can be some connectivity in the netlist which may later create problem in design for test or ensuring the testability of the design. So, those kind of constructs can be flagged by these rule checkers, right. So, these are some of the verification tasks that we need to carry out during VLSI design flow. Right. Now, let us look into another aspect of VLSI design flow, that is related to testing, right. So, till now we have discussed the design flow, meaning that we are making changes to our design and we have got the layout, right. So, now we have carried out the verification steps in this part, right, in the designing part, right. And what verification is doing is that it is ensuring that the final layout that we are getting, or the GDS representation of our design or circuit, is correct, such that the original specification is met, right. So, whatever the original specification was there, that is met by the met by the layout, right. That is what we mean by the verification task, right. Now, once we have done the verification, we have got the final layout, we give this layout to the founder, right? We give this task, this layout to the foundry for fabrication. Now, after fabrication, when we get these chips, how to ensure that the chips were actually having the features that were defined in our design layout, right. So, there can be some problem in creating this chip, right, and how do we catch this? So, we catch such manufacturing introduced defects or problems in our circuit in a step which is known as testing or manufacturing test, right. So, the testing ensures that the fabricated chip does not have any manufacturing defect. So, we should understand the difference between the verification task, which is carried out during the design step, and the testing or manufacturing test task, which is carried out after fabrication, to ensure that whatever the chip has been fabricated, that is meeting the original layout, right, or original design that we started with the fabrication, right. So, the purpose of both verification and testing are different. But then why should we consider testing during designing also, right? So, we need to consider testing during design step also, because during the design step, that is from the RTL to GDS step, during this step we can introduce features in our design which allows easy testing, right, or easy finding problem in our fabricated chip, right. So, testing is very important during the design phase. Why? Because we need to add features in our design which will allow the later on the manufactured chip to be tested. If we don't carry out those kind of modification or add features to our design, then testing will become very difficult, right, and therefore, the testing needs to be considered during the design step also. And RTL to GDS flow ensures that if some defect is found, then the problem can be easily diagnosed and debugged, and if required we can fix some problem, right. So, therefore, testing is very important even during design step, right. However, testing is actually done after we have manufactured the chip, and we want to do this kind of testing so that we recognize or identify the chip which has defect and which has been not manufactured as per given layout. We can identify that and disallow those chips to reach to the end customer or end user. So, what is a defect and how do these defects originate? So, defects are physical imperfections in a fabricated chip and they are of permanent nature, right. So, how are these defects introduced in the first place? We actually carry out this fabrication in a very sophisticated environment which is known as clean room. So, in clean room, the particulate impurities, those are very well controlled, right. Also the static electricity and even vibrations, those things are very well controlled inside this clean room. Then even despite the manufacturing being very sophisticated task, how do we get defects in our chip, right. So, the defects originate because of many reasons. Some of them are statistical deviations in the material properties, maybe the materials that we use in fabrication, maybe the chemicals, those may have some statistical deviations, right. For example, the concentration may not be exact, but have some deviations in the concentration of say the acid that we are using in our manufacturing, or there can be finite tolerances in the process parameters. For example, the furnace temperature, if we say that it is 800 degrees Celsius, it may not be exactly 800 degrees Celsius, it may vary between say 800 degrees Celsius plus minus 1 degree, right, just an example for it, right. And there can be airborne particles and undesired chemicals. We try to reduce it, but cannot always eliminate them, right. and those airborne particles and undesired chemicals can lead to defects in our chip, and also there can be deviations in the mask features which can lead to defects. Now, there are two kinds of defects. The first one is the large area defects that can be created by, say, wafer mishandling, or by, say, misalignment of various masks and so on. So, those are basically simpler to eliminate, and in advanced process or in matured processes, those large area defects are easily eliminated, right. But there are spot defects or small area defects which has random nature, and those inevitably appear in chip during fabrication. So, the spot defects increase with the increase in the area, and these spot defects are the primary concern for testing. Now, how are these manufacturing defects manifested? So, the manufacturing defects can be manifested in many forms. One of them can be, or the most common is, a short circuit of the lines or the open circuit of the lines. For example, suppose there were 3 lines and the ground line was running together, and a conducting particle came and sat between this line C and ground. As a result, C and ground will be shorted. So, this is a short circuit defect. Similarly, if there is a non-conducting particle, it can break this wire or the path of this wire, electrical path in this wire, and signal A is open circuited. There can be other defects which can change the circuit parameters, and as a result, say, delay can increase or decrease, and this can lead to problem in the circuit, right. And a point to note is that there can be distortions also in our fabricated chip, and this distortion can be due to optical effects such as diffraction and so on, while this diffraction effects, while we are carrying out photolithography, this can distort the image that we form on our substrate, and therefore, the features will be slightly distorted. It may not be perfect rectangular shape or so on. So, these kind of distortions needs to be handled by some way, because these are inevitable, we cannot avoid them. But the point to note is that testing does not involve detecting these kind of distortions. So, the focus of testing is not looking into these distortions, right, distortions of the features. These distortions are inevitable and needs to be handled using some techniques. Some of the techniques we will be looking in the next lecture, and there can be inconsequential flaws also. For example, suppose the size of this dust particle was very small, right. So, even if this dust particle was, or conducting particle was there in our chip, it will not lead to any observable change in our chip behavior, and these things, these inconsequential flaws in our chip, those are also not the focus area of testing, right. So, the testing does not detect these inconsequential flaws, right. So, the testing do not detect distortions and inconsequential flaws. Then what does testing detect, right? So, testing detects faults, right. So, testing focuses on finding defects that can be problematic for a circuit behavior, and the defects are modeled as faults in our circuit. For example, we can model this conducting, or this defect of conducting particles sitting between line C and ground by a fault which is known as stuck-at fault. We can say that this line C is stuck to 0, right. It is stuck to 0 by this fault, right, by this defect. So, we model defect using faults, and the purpose of testing is to detect those faults, right. Now, let us also look into that what are the effects of having defect in our chip. So, the first effect is that there will be yield loss. Now, what is yield? Yield is basically the fraction of die on a chip that are good or without any fatal manufacturing defect. For example, if there are say 300 dies, right, sorry, if there are, we are manufacturing 400 dies and out of them say 300 dies are manufactured good and 100 are having some defects, then we say that the yield of this process is 300 divided by 400 into 100 is equal to 75%. So, this is a fraction of die on the wafer that are good expressed in percentage. Now, on what factors yield depend? So, it is a function of complexity and maturity of the process. If manufacturing process is mature, then typically the yield will be more than 90%, and for a recently developed process, the yield may be lower than even 50%, right. So, depending on the maturity of the process, the yield may be lower or higher, right. There are other factors which affects the yield, and one of the most important factor of a chip is the die area, right. When the chip area or the die area increases, then the probability of having a defect on the chip increases and therefore the yield comes down, right. Similarly, the defect density is basically a function of the process technology and how matured it is. So, the yield will depend on the defect density. It is defined as the average number of defects per unit area of chip. And the third important factor which impacts yield is the clustering. Now, what is clustering? Clustering is basically defining how the defects are distributed over a wafer. So, let us understand that how clustering can impact our yield. Consider that there is we have a wafer in which we are fabricating say 34 dies. So, these are 34 dies we are manufacturing, and in one case the defects are distributed all over the wafer. So, this is the case. Now, in this figure these red dots mean is that the wafer, that particular die is having a defect, right. Now, there are 10 such dots, meaning that 10 dies are having defects and rest are having or the rest are defect free, right. So, in this case what will be the yield, right. So, in this case the yield will be 34 minus 10 which are defective, that is 24 divided by 34 into 100%, that is 71%. Now, let us look into another fabrication process in which we had the same number of red dots, but those are meaning that we have the defects, same number of defects, but those defects are clustered in a sense, right. So, defects are lying in a smaller region, right. So, the number of defects are same, but it is distributed over a smaller area in this case. Now, in this case what is the yield, right. So, there are 26 dies without any red dots, meaning that they are defect free, and therefore, the yield is 26 divided by 34 into 100, that is 76%, right. So, in this case the yield is higher, meaning that if the defects are clustered on the wafer, right, then the yield will be higher. Why? Because whenever a defect is on a die, adding more defects on the same die does not lead to extra yield loss, right. So, if the defects are clustered in a technology, then that technology will have more yield, right. So, fortunately what happens is that in the fabrication of chip, these defects are found to be clustered in groups or over the region over the wafer. Now, when we start a chip designing venture, we need to decide or understand that what will be the profitability of our venture. And in this equation or in this analysis of profitability, yield is a very important criteria. Why? Because if yield is low, less number of wafers or less number of dies can be fabricated for a given wafer area, and therefore the effective cost of the chip will go high and the profitability will go down, right. And therefore, before starting a venture, we need to understand or have some estimate of what the yield of that chip will be, right. And to do that, we need to understand the yield models. We need to have some understanding of yield models, and in literature there are many yield models with varying degree of accuracy and computational requirement. One of the popular yield model is based on assuming that the probability of having a defect in a given area increases linearly with the number of defects, right. And this is because of the clustering, right. If we assume this, then we can arrive at a yield model which is shown here. So, yield y is equal to 1 plus a is the area of the die, d is the defect density, and alpha is the clustering parameter. Now, let us understand that how does this yield change with clustering, right. So, to do that, we assume that AD is equal to 1, just for the sake of understanding this equation. If we put AD is equal to 1, then what happens is that this equation boils down to 1 plus 1 divided by alpha raised to the power minus alpha. And if we plot this equation, we will get this curve. So, whenever the clustering parameter alpha has a low value, it means that the defects get clustered in a very narrow region, and as a result of that, very less number of chips or dies are being impacted, and the yield is very high. And if it is distributed all over the area, meaning that when alpha is very large, then there is a high yield loss, right. Now, how can we use this formula or the yield model for arriving at the yield value for a given chip? Now, based on historical data, for a given technology, we can arrive at this number d, defect density, and the clustering parameter by curve fitting. And once we have this parameter d and alpha, we can use our estimate of our chip area A, and then we get an yield out of it, right. So, we can get an estimate of yield using the chip area and the past estimates of or past data of yield, and using curve fitting we can get these parameters d and alpha, right. So, this is how we can use the yield model for computing yield and maybe the profitability of our venture. Now, how is testing done? So, testing is done using an equipment which is known as automatic test equipment. This is the most important equipment in testing. So, this testing technique that I have shown is a testing technique which is based on automatic testing equipment, and this is one of the testing paradigms. There are other testing paradigms which we will be seeing later in this course. So, in this testing paradigm, what we do is that we apply test vectors or test patterns to the fabricated die with the help of automatic test equipment. Now, this automatic test equipment has got test head, probe cards, and probe needles. So, what happens is that there are needles which are there in automatic test equipment, and those needles basically go and make contact with the wafer, and because of that contact, then electrical path is made, and through that electrical path a test vector or a 0 or 1 can be applied to the die, and through those needles only the values can be read out from the die, and what the value it produced, it can be read, right. So, now there are test programs in this automatic test equipment which basically controls all these operations. What does this test program do? it will load the test patterns, and if these test patterns will be applied to the die through the test needle, and then it will observe the response again through those probe needles, and the actual responses will be compared with the expected response. If they match, then we say that it has passed the test. If they do not match, then we say that it has failed the test. Now, these test patterns are designed or are arrived at by considering our design functionality such that if we apply this test pattern for a given fault, the good circuit and the bad circuit, meaning a circuit which has got defect, will produce different output response. And by observing the response, and if those responses are different, we can say that there exists a fault in our fabricated die, right. So, this is the basic technique of test pattern based testing or manufacturing test, right. So, if we get a failure in a chip, then we may like to diagnose it and find the root cause and fix the problem. And then if diagnosis corrective measures are required, then we can take that and reduce the effect of the defect in the subsequent fabrication flow, right. Anyway, the way the failed die, those will be not going to the next part of the design process, and those will not reach the end customer or end user, right. Now, in this automatic test based testing, automatic test equipment based testing, we apply test vectors to our manufactured chip. Now, how do we measure that the test vectors that we are applying are of good quality? We measure it using a parameter which is known as fault coverage. Now, what is fault coverage? It measures the ability of the set of test patterns to detect a class of fault. So, fault coverage is equal to number of faults detectable by a given set of test vectors divided by all possible faults in the circuit, right. So, fault coverage is a measure of quality of testing. Ideally, we want that the fault coverage should be 100%, but that is very difficult to attain, and practically we try to get it typically more than 99%. Then what it means is that if we leave 1% of faults undetected, that may be actually be there. It may happen that some chips can pass the test and still go to the customer, and those are actually defective. Why? Because those contain defects which were not tested. Those are those 1% which was left untested, right. So, the perceived quality of a chip based on the customer will depend on how much fault coverage we are doing. If we are 100%, then no chip can escape testing, right, or no defective chip will escape testing. It will always be caught, and it also depends on yield, meaning that if yield is 100%, then all will be error free, right. So, if yield is high, then the chip will not have the defect and the perceived quality of the chip will be very good, right. So, quality of chip is measured by a quantity which is known as defect level. So, what is a defect level? It is the ratio of chips that are bad or faulty among the chips that have passed the test, right. So, typically it is measured in parts per million. So, let me give you an illustration. Suppose we are manufacturing 100 chips, right. Now, let us assume that the yield of the process is 90%, and therefore, out of this 10% or 10 chip will be bad and 90 chip will be good, right. Now, let us assume that fault coverage for the sake of argument is just 50%, right, 50%, not 100%. Ideally, it should be 100%. Suppose it is 50%. Then out of these defective 10 chips, 50% will be caught because those will be containing those 50% defects, right, which is being tested by the fault by the test patterns, and rest 50% will escape the testing. Those will contain the fault, that those will have the fault, but those will not be captured by the test pattern, and therefore they will go undetected. So, 5 chips will go undetected, 5 bad chips will go undetected, and 5 bad chips will be caught, and those will be eliminated, or those will not reach the end customer, right. So, 5 will not reach the end customer, those are discarded, and 5 will be considered good, right, because the fault coverage we are assuming is 50%, right. So, the number of chips that will reach the end customer will be 90 plus 5, that is 95, and out of this 5 will be actually defective, right. So, defect level will be 5 divided by 95 into, we are measuring defect level in terms of parts per million, we multiply with 1 million, and this is what the defect level will be for this process. Now, defect level is the measure of effectiveness of the test. If the testing is fully effective, then DL will be defect level will be 0, meaning that these 5 will also be caught during testing, and only these 90 chips will go to the customer, and therefore the defect level will be 0. For commercial chips, typically defect level is less than 500 parts per million, right. So, now in this we saw that the testing is actually done after doing the manufacturing, right. But why should we be concerned about testing during design phase? Because we need to carry out a lot of design steps which are targeted for test, and those design steps are known as design for test, right, or DFT. So, what are those tasks? The first task is to insert logic structure inside our fabricated die such that testing becomes easy. The second part is to get good test patterns which will be actually be able to detect faults or differentiate between a faulty and a fault free circuit. And third is that what should be the expected response from a good circuit, that we need to get that information during the design phase. So, these are some of the tasks that needs to be carried out during the design steps, and these are intended for manufacturing test. We will discuss this task in detail later in this course, right. So, this is the reference which can help you go deeper into this topic. And so, let me summarize what we have discussed in this lecture. So, in this lecture we have looked into 2 important parts of design flow, that is verification and testing, right. And so, we have now covered covered our design flow right from idea up to the layout. We have covered the implementation of the design, we have covered the verification of the design, we have also covered the testing of the design. We have taken an overview of all these processes. In the next lecture, we will be looking briefly at the fabrication step, meaning that once we get a layout, what is done in the foundry and how do we get the final chips. So, thank you. This is the end of the lecture. Thank you very much.